Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. Okay, step inside, and we are wrapping up our trigonometry set, at least for what I'm going to do here in the basic trig functions. Everything's an overview of what we've done before. In my last video on the trig stuff was a non-calculator portion of the material, and this is calculator portion of the material. A lot less on the unit circle and a lot more on things within a triangle. Law of sines, law of cosines are a big heavy part of this one right here. And so more on the word problem graphing, only a calculator version of it, something you could only do in a calculator, something that's just harder, I guess, because the other one I guess would have been easier in a nutshell. So I'm going to give you that with a, I forget how many problems here, not too many, it's a front and back sheet. Again, for my kiddos, as I generally do. So I'm going to go ahead and get into it. Make sure you have your calculator handy, and make sure you know how to switch to modes of degrees and radians as needed, and really when you're supposed to do it. And my calculator always defaults to radians, so I'm going to have to switch degrees pretty soon. All right, first problems here. Find each measurement indicated, then find the area of each triangle. Don't let me forget to do that, because I'm sure I could. Round your answers to the nearest tenth. And for the most part, outside of maybe the area portion, for the most part, they tend to land as integer answers the way that they're set up here. All right, the first one, we want to find the measure of angle A right here given this information. Now, what we have set up right here, if you look at this, is we have a known angle measure here on B and the side opposite. We're trying to find this angle measure right here, and we know its side opposite. This is a classic law of sines case, and we haven't seen these for a while, perhaps together video-wise. This is some form of, if you want to find the angle, probably put it on top, some sort of sine of A over A equals sine of B over B scenario that we want. By the way, sine of C over C would be the same thing. And when I say A, B, and C, I don't mean them literally, as in they could be different letters. They could be X, Y, Z, whatever it is. But just keep in mind that this is a correct proportion for all triangles, so we can use this and set it up. Now, that is what you would want to do to set this up and solve. However, if you jump the gun too fast and start to go by process more than anything else here, then you're missing one big picture about this problem. This is a 90-degree right angle. This is a right triangle. And if you know anything about right triangle trig, I can guarantee you that my integrated math 2 students can solve this question better than my integrated math 3 students, because they're used to right triangle trig. Set a straight up basic idea that when you have this angle A that you're trying to solve for as a measure, the opposite side of A and the hypotenuse of the triangle lends you to use a sign, that the sine of this angle A equals the opposite over the hypotenuse, and then to solve for A, you take the inverse sine of both sides. A is the inverse sine of 30 over 35. Now I will go to my calculator here, I will determine what that is, and don't worry, I will do this in a law of sines way, just because not every problem is going to be like that there. So I do need to make sure that I am in degrees for this thing here, because we are referring to the degrees of a triangle here. So I'm going to do the inverse sine of 30 over 35, and this should give me the angle measure for A. See, that's an example right there, 58.997, 59.0 degrees there, excuse me. So 59.0 degrees, like that. Now, I'm not saying that you can't solve it using law of sines. I'm going to do it right now. I'm saying that you're overthinking the problem when you have a right angle staring you straight in the face. And I bet if I didn't have this right here, some of my students would say, how do you solve this thing? It's your SOHCAHTOA stuff. We're going to have to know how to do that. Now, this is 90 right here. And if I use the law of sines doing the exact same kind of things before, I could say sine of my unknown A that I'm trying to find over, now you want to use the side opposite here, over A, which is 30, equals sine of B, sine of this 90 over B right here, 35. So when you multiply both, because you got to solve for A, so when I multiply both sides by 30, I'd get sine of A equals 30 times sine of 90 over 35. And then you go ahead and take the inverse sine of both sides, and you get A equals the inverse sine of 30 times the sine of 90 degrees over 35. And then if you use the calculator, I'll just tell you what, if you use the calculator, you're going to get the same answer that we got right here. You can get 59 degrees. Now, why, Mr. Robinson, why does this work the same way as the other thing? Well, if you learn my law of sines proof and how it works, it all starts with building an altitude and working some angle up. This is how you work it out. But then the other question is, Mr. Robinson, why are they the same answer? Like, literally, why is it when I calculate this and this, they're the same thing? Well, let's investigate. What's the difference between these two setups right here? This one has a sine of 90 being multiplied, and this one does not. Wouldn't that change the number if you multiply by the sine of 90? Yeah, unless the number's 1. The sine of 90 degrees is 1, right? And my students should know that the sine of 90 is 1, whether they drew it in their period table things or whether they've been using quadrantal angles. The sine of 90 is 1. So 30 times 1 is what you get there. So actually being 90 degrees doesn't change the answer. Regardless, you still get the answer. This is the way you're generally going to want to set it up because you're not expected to see a 90 degree thing here. But don't overthink a problem that doesn't need to be overthought. Every student who has done trig should be well aware of how to solve angles in right triangles, and that's just one of them. I wanted to call attention to all that. Okay, number 2. Find the length of BC right here. I'm also going to call it just A, lowercase a right there, because it's opposite the angle A. Now this one, I have this angle opposite, and I have this side here. I have this angle, don't know this side opposite. I have this side, don't currently know the angle opposite. I think we can find that pretty easily. And if you're asking yourself, can we use law of sines here? You can if you do know an angle opposite its side and the side itself, And then you need to find a side opposite an angle that you know. This is not a law of cosines problem. Law of cosines requires at least 2 sides to be known in the angle in between, or all 3 sides to be known. And this is not that. So you got to do something, otherwise we can't solve it. And we do know that the interior angle sum of a triangle is 180 degrees, which is something we're going to go off of. The measure of this angle here is going to be 180 degrees minus the sum of 43 and 103 right there. Oh, by the way, I never found the area of this triangle. I got to go back and, you know what, let's go back and do that. Why don't we save those all to the end? I'll do the area of the triangles all at the end, and so it'll ring familiar with what I'm doing in each one, or we get to look at what the case is involved with all of those 3. Because there's probably still more I'd have to do with this one to work it out, and we have options. Okay, 180 minus 43 plus 133, so that's 180 minus 146, I don't need parentheses, which is 34? Which is 34 degrees. So this B is 34 degrees, which now lets me do law of sines here. I know angle and side opposite. I know this angle. I need side opposite. Now, using this law of sines thing here, I need to find this A. I want to kind of flip these fractions here and put the A on top so I'm not doing more work to try and get that A by itself. So I'm going to do A over sine A equals B over sine B, like that. The A that I'm trying to find, A, over sine of angle A, which is 103 degrees, equals B, the side opposite the angle, 23, over the sine of that 34 degrees that we just found right there. So multiply both sides by sine of 103, and that's kind of all you have to do before the calculator. A equals 23 times the sine of 103 degrees over sine of 34 degrees, like that. So what is that approximately? This one I do not know. I know it's going to be the largest of these. It's going to be larger than this. Let's go to the calculator. Give me one moment. Where's graphing calculator? Okay. So let's do 23 times sine of 103, all divided by 34. Oh, excuse me, sine of 34. Let me do that one more time. Over sine of 34. Yeah, that doesn't look right. Oh, not divided by. I'm sorry. Let me do this again. I hit a divided by button that never should have been. 23, Okay, there we go. All right, so yeah, don't just trust an answer when it says, hey, this is going to round differently. This is 40.1. So A is about 40.1 units in length here. Okay. So those are the first 2. There are 2 more to do, and I will be finding area of all of them, but let's also write the 40.1. It may be good use. Now, 40.1 does have an exact answer as well. I might want to consider kind of holding it in mind. I'm going to store that thing. Give me one sec. Go to the graphing calculator. Let's store this into, let's store it into A right there. So when I recall A, that's where it will go. I'll just have to remember that. Okay. Let's move forward we have now find the length of BC, which is also opposite that A, again right here. Now in this one here, I'm trying to find the side I know the angle opposite, but this is the only angle that I know. With this side I don't know angle opposite, this side I don't know angle opposite, and I can't get those either. There's not enough information. I don't have two angles to get a third. This is not a law of sines problem. In fact, it's a law of cosines problem. The law of cosines is best used when you are, how do I say, you have two sides in the included angle, the angle in between, to find the side opposite that angle right there. This law of cosines formula, when I write C, it's not with the intent of the A that's right there. So I'm going to write what I generally write for the formula. If you'd like me to rewrite it, I totally will. But don't take it literally as in C, like opposite this 30 right here. But C squared equals A squared plus B squared minus 2AB times the cosine of the angle, C, capital C right there. That's the formula right here. So when I say C, what I'm referring to is the side opposite the angle that I know. You can see this is lowercase c, uppercase C. We should know all of these values here, which is A and B, two sides that are not the side that I'm looking for. So this side and this side. There's the A and B again. And then the C is the angle opposite the side that I do know. So I'm using those ones. And I know it's kind of weird because, you know, I'm using letters different from what it was. So I guess literally the way I could put this is A squared equals B squared plus C squared minus 2BC times the cosine of A. Yeah, I could do that. And some books rewrite it that way. But listen, not every triangle will say ABC. Mine do. I'm talking out loud in that way because I know that a lot of students tend to kind of mix that thing up and say, am I supposed to use C? No, my diagram was always like this. And actually, I should have done this to start with. My diagram was always like this. Given that you are having two sides in the angle in between and you're trying to find this, this is what you would do. So that's what we have here. This is law of cosines. Let's go. A squared is my C squared equals that A squared, what is 17 squared plus 30 squared minus 2AB, or 2BC. 30 times the cosine of the included angle, which is 32. All right, so that is going to be, a lot of this I kind of like to do in my head, and then I have to use the calculator after. So 289 plus 900 minus 2 times 17 times 30, 34 to, oh boy. 70 is 51. 1020, I think. I don't want to be wrong on that. I think 1020, and this is 1189 minus 1020. I'm going to double check that part. 2 times 17. Oh, you know what? That's right. I think that's right. Okay, so we're going to go to the calculator here for A squared. You have to remember this is only A squared. In order to find A, we're going to have to take the square root of both sides after, right? Take the square root here, take the square root there. So A, and yeah, don't round early. I'm not going to do that. I'm going to do square root of this whole thing. So let's check it out. Square root of 1189 minus 1020 times the cosine of 32. All right, 17.999, looking at 18 centimeters because it does have actual units on this one here. So this is going to be about 18.0 centimeters. Keep in mind we're still going to have to find area on this thing here. So 18.0. Okay, let's go ahead and do number 4 and find the measure of angle C. Now, angle C is this guy right here. And as you can tell, we do know the side opposite, maybe a law of sines thing, as long as we know an angle and side opposite, which we don't there. We know the angle but not the side. And here we know the side but not the angle. And because we only have one angle, this is a lot like this problem here, right, basically. So it's a law of cosines thing, only we're not trying to find this length right here, this opposite B is B. We're trying to find the measure of the angle. But if we found that B, we could use that to find the measure of the angle. You have one of two options to find that. I'll explore both of them, but I'll probably solve just only using one of them ultimately. So let's first find that B. Let's use law of cosines like we did before here to say B squared equals this A squared plus B squared minus 2AB. Oh, not literally A. Minus 2AB times cosine of C, cosine of 36. And this will be 225 plus 529, which is 754. 754 minus 30 times 23 is 690. 690 times cosine of 36. So that's the b squared. Take the square root of both sides and you'll get, b is whatever that's going to be. Let's go ahead and check that one out. Graphing calculator. Let's go to square root of 754 minus 690. Just got hit. 690 times the cosine of 36 right there. And that's 13.99, just around 14 there. So b is around 14, and this is kilometers for us here. So 14 kilometers. I'm going to go ahead and erase the b and put the 14 right there. Now, it's not exact, and I need to use this length still in some capacity. I'm either going to do law of sines now, which I won't actually do it this way. I want to show you a different way. But I can do sine of c over c equals sine of b over b. What's b? Wait, sine of b over 14. So you have to kind of use that 14 in that kind of way eventually anyway. And this is one version of what you could do. Now, one of the reasons, generally I like to use law of sine, but I generally like to use law of sine after I use law of cosines to find something. And the reason is because inverse sine cannot give us obtuse angle measures. And, if we do solve this thing right here, actually, if I multiply both sides by 23 and take the inverse sine, I'm going to get the inverse sine of, I guess I am solving this way, but I want to caution you about right here. 23 times the sine of 36, all divided by 14. And this is 74.93. But the problem with that is when I say that angle is this, it's not, we can't assume it's drawn to scale, but you have to understand that some angles can be obtuse. And I'm going to assume that this one kind of is an obtuse angle. I could tell you it's probably around 115 degrees based on what I'm seeing with the 74 thing. It's probably around 115 degrees, but your calculator doesn't show that. Right, your calculator doesn't show that. This is one of those two triangle cases. We'll talk about ambiguous cases in a second. This is kind of one of those two triangle cases, and this is the one where you have an obtuse triangle. And what I'm bringing up right now is, using law of sines can't give you obtuse angles, but law of cosines can. So although we set something up, we have an angle that would work for one of our triangles. You might not understand or realize why this isn't necessarily the second triangle. So you could also alternatively find A first instead, and then subtract those from 180 and you get C. Or you can use law of cosines here in kind of a rewrite of the law of cosines equation, getting the cosine of C by itself here, if this is one of our equations. The other one is cosine of C equals A squared plus B squared minus C squared over 2AB. As if to say that the angle C has this side C that's opposite, which is the squared one that's subtracted, and it doesn't exist in the denominator right there. Okay. So I'm going to go ahead and use that one. Inverse cosine does give you obtuse angles, and it has a little to do with the periodic function things that we do. So let's do the cosine of our angle C here equals, now this has to be the side opposite the angle that we're trying to find, the 23. So I got to do some sort of 15 squared plus 14 squared. Remember, that's a rounded number. Minus 23 squared. All over 2 times 15 times 14. Okay, now that 14 wasn't an exact 14. I'm going to go and revisit that value for myself right there. Okay, so I'm going to calculate all that, and I'm going to take the inverse cosine of that. The inverse cosine of. So this is going to be, I'm going to round this a little bit. So 225 plus 196 is 421 minus 576. Let me do that. 421, or minus 529, I should say. Minus 529 is negative 108. So negative 108 over 2 times 15 times 14. I'll tell me what that is. 420, I think. So I'm going to do the inverse cosine of that right there really fast. Just take my word for it. Negative 108 over 420. I hope the math was done correctly. And I'm getting 104.9. Didn't I say I was going to be around? I said 115. I must have meant 105. Around 105 degrees right there. So it's approximately, I was trying to do 180 minus 7.5 and I couldn't do it. So it's around 104.9 degrees right there, and that is the measure of that angle. Okay, that's the measure of that angle right there. Okay, so we found what we were looking for on problems 1 through 4 outside of finding area. So we still have to find the area of each problem here. Let's go ahead and do exactly that. To find the area of these triangles here, it's kind of the same as Law of Cosines when it comes to setup. I feel like I gotta sneeze. Where if you knew two sides and the angle in between, and there's a way that we came up with these areas together, as a class in these videos. It's 1/2 AB times sine of C, like that. That's the area there. So I'm gonna go ahead and find area in all 4 of these right here. Let's start with this one. You do need 2 sides and the angle in between, so I can either use these sides and get this angle in between, which I totally can. We know that A is around 59 degrees right here, so C is around 31 degrees. If you want the exact, we can come up with it still. We just got to do the inverse sine of 30 over 35. And then 90 minus that 59 to get it. So inverse sine of 30 over 35 is around that 59 value, and 90 minus that number. So I have an exact version of this answer that's right there. This isn't the area yet, that's just the angle. So I have the angle exact number. And we are going to go ahead and do that 1/2 AB times sine of that angle right there. So area is 1/2. AB is like your 30 and 35 and 30. 35, 30 times sine of that 31. Again, I have an exact version of it. So this is going to be about 1/2. I'll let you see this. Of 35 times 30 times the sine of 31. Oh, the previous answer right there. So 270.4 square units. 270.4 u squareds right there. All right, that is that angle A. Or area, not angle A. I just said A, and that's the area. Let's find the area of this one right here, where we have this side length, this angle in between. I'd like to work those ones out, even though we had to approximate this one. I think I stored this value for us before. So this area, oh, you can't see what I'm writing. I'm so sorry about that. What I wrote up here was 1/2 35 times 30 times sine of 31, which is 270.4 square units. So the next one right here, I should probably use the 23, 43, and 40.1 because I know those two sides. I know the angle in between. So this area is going to be 1/2 times A times B times sine of C, like that. So that 40.1, I think I saved it. So 0.5 times 40.1 is stored as A times 23 times sine of 43. And I'm getting 314.3 square units there. I dare not switch to the calculator after switching off this screen and leaving it off. I will again eventually. All right, find the area here. Now these two problems were very set up for this because you did have two sides and the angle in between already. So I'm just going to use those. So 1/2 times 17 times 30 times the sine of 32 right there. Take my word for it in the calculator. 510. 17 times 30 times the sine of 32. 135.1. Now this is in centimeters, or square centimeters. And the last one, area is 1/2 that stuff. So 1/2 15 times 23 times sine of 36. Was it 15 and 30? Oh, 23. 15 and 20. Okay, let's do that one right there. And that's going to be 0.5 times 15 times 23 times sine of 36. Is 101.4. It's around 101.4 kilometers, square kilometers. All right, that's the area talk on those 4 right there. And that covers up all the triangle ones I wanted to do. Questions? Okay, let's move on. All right, so now we're going to do the state the number of possible triangles can be formed and indicate how you know. These are angle side cases right here, where if I have some sort of angle A, like this 146 degree, beautiful angle, 146 degree angle A, the side length opposite the A is the 34. Now 34 is not quite 35, right? This is a 34-inch mark, and here's a 35-inch mark that I could represent as C, as long as it's this side or that side here. Does this have enough length in 34 to come back and reach and make this thing right here? Well, not if it's 34 and this is 35, right? 34 is less than 35. How can I fit that back and make a triangle? That 34 side opposite is less than the 35 right there, so no triangles can be formed in that scenario. It's just not possible to reach. Okay, the next one, we have an acute angle right here that's 29 degrees, maybe something like that right there. This B is 29 degrees. Okay, the side opposite the B is the 15, and this A is 28. So let's say I had A be this guy right here. So A is 28 kilometers. This B is 15 kilometers. Now B is significantly less than 18. As if to say, if it was more than or equal, 28. As if to say, if it was more than or equal to 28, it would definitely join up and be able to connect and make one triangle, which is a single triangle. This is less than 15, so maybe it's not even enough, given this angle and this side length, to go back and reach here. But if it is, it might be twice the ability to hit right here or right here, right? So it could be 2 triangles, all depending on how big it is. And the question is, how far does it have to reach? Well, the shortest height you can have, if I call this some h right here, shortest height you can have can be found using sine. So we can say sine of 29 equals h over 28. And multiply both sides by 28. H is 28 times the sine of 29, which is about 28 times sine of 29. 13.57 kilometers. So the only question is 15 more than 13.57? The answer is yeah, it is. The 15 is longer than this h right here, therefore it could hit probably like right there and right there. It could make a triangle like this, and it could make a triangle like this, as of course this side can shorten itself up into like that. So there are 2 possible triangles that can be formed there. So 15 is more than the 13.57. The B is longer than the h. So 2 triangles in that scenario. Okay. Now this is kind of unit circle-ish based here. Find the exact values of the trig function indicated. Reference angle, angle of rotation, sine of theta, and tangent of theta. We know that the cosine of some theta is negative 0.1961, and sine of theta is less than 0. Well, this is negative for cosine. This is negative for sine. And the only quadrant that has negative cosine and sine in it is quadrant 3. I'll put Q3, like that. So in quadrant 3, it says find the reference angle and the angle of rotation. The reference angle is going to be some sort of, if I put x, it's going to be some sort of x right here. It's the angle that's actually built inside. Now I'm going to use inverse cosine to determine that. I have some adjacent over hypotenuse to get myself this ratio. It's negative, by the way, because it's in this quadrant. When I do inverse cosine, I'm just going to do inverse cosine of the positive value. I want a positive x. The angle of rotation, if I called it some sort of theta, as this kind of is right here, the angle of rotation is how far is this rotation right there to get to the terminal side. How far is the theta? So let's start with the reference angle right here. Let's do the inverse cosine. X is the inverse cosine of positive 0.1961. This is all about reference angle to start right here. So I'm going to do the inverse cosine of 0.1961, and I'm going to get 78.69. I'm going to go ahead and round this to the, it says find the exact values. I think that's for these, the trig things. Oh, you can't see what I'm talking about. I think they're talking about these for the exact values there, which I will use. But I have that 78.69 number. or the reference angle right there, I'm just going to call around 78.7 degrees. Now, the angle of rotation theta is this whole 180 degrees plus this right here. This accounts for quadrant now. So angle of rotation is 180 plus the 78.7 degrees, which is around 258.7 degrees, like that. So that's what those two are right there. Sine of theta and tangent of theta, what I'm going to do is take sine of my angle right there. Okay, I'm going to take my sine of my theta right there, and then I'm going to make it negative. And then I'm going to take tangent of it, and I'm going to make it negative. And I have the exact value right here, where I get to do sine of this angle right here. Oh, not L3, of this previous, sine of the previous answer right here. And I'm going to get 0.9805 or 06, around 0.9806. And then I'm going to take the tangent of that previous angle as well, tangent of the inverse cosine of 0.1961. That's going to be 5.0004. So around 5. But if I want to round to 4 decimal places like this one was, oh, by the way, these are also going to be, tangent's going to be positive. I don't know if I accidentally said sine and cosine. Tangent's going to be positive. Sine is going to be negative because in the third quadrant, sine is negative, like cosine is, but not tangent. So there's sine, there's tangent. We're done. Okay, the last problem here, number 8. According to the National Weather Service, this year, the city of Sacramento will have 15 hours of sunlight on its longest day of the year, which is June 21st, my birthday, 171 days after New Year's, and 9.5 hours of sunlight on its shortest day of the year, December 21st, 354 days. Is that another comma that's not supposed to be there? I think so. 354 days after New Year's. Let t equal 0 represent New Year's Day, January 1st. So here's January 1st. Here must be January, I guess 21st, because it's 20 days after, right? So we're going to draw a graph based on this. We have a height on the 171st day. These look to go by, well, these look to go by 5s. 5, 10, 15, 20, like this. So 171 days is, here's 160. This must be 170 right here. And 171 has, I thought I saw 15. There it is, 15 hours of sunlight on 171 days after the fact. So about right there. Okay, and then the lowest is 9.5 hours. Here's 9, here's 10, and that is 354 days into the year. So the lowest this thing gets is actually right here, 350. 350. So 354 is probably about there-ish. And that's a low. Now, in between, because this is half of a period, because this is a peak and this is a trough, that means that there's something the other way that I could find and plot in that would give me another thing to complete the period by, right? The period is a certain number of days. This is where a calculator can be useful for us here. We know that the difference between December 21st and June 21st is day 354 minus day 171. So that distance between these two is 183. That means there's another 183 days before June 21st where we can plot another point. I'll have you know it ends up being a negative value when I think about it. That's going to be 171 minus 183 minus the previous value there. I'm going to get negative 12. This is a point on a graph that's basically 12 days before New Year's. And I know that's not part of this year, but it can help us still build our model. So negative 12, that's not negative 12, that's negative 5, negative 5, negative 10. So, right at there. At negative 12, we also have a point. Now, what's in between on this period right here? If 183 is half the period, and that kind of makes sense, because if 183 is half the period, you double that, that is 366, which is how many days there are, well, in a leap year. But it's about, instead of 365.25, that's, I think we're going to just live with that, how many days there kind of are in the year. Now, when we divide this by 4 right here with this period, this is how much is in between each of our days on the midline at 91.5. Now, I didn't get the midline for us yet. Midline is half the distance between 15 and 9.5. So to get half that distance, you average those numbers. 15 plus 9.5 over 2, which is 24.5 over 2, which is 12.25. 12.25. So I'm going to draw a midline at 11, 12, about around 12 and a quarter, right? About there-ish. And I'm going to thin it up like that. And yeah, that's fine. So there's my midline right there. So on my midline, there's going to be points that are 91.5 days away. That's what I calculated before there. So what's 91.5 days from negative 12 or from 171? Let's go to the calculator there and let's check out negative 12 plus, well, it should be 80, it should be 79.5. Negative 12 plus 91.5. 79.5 right there. So I'm going to plot a point on the midline at 79.5, really close to 80, just about right there. And then another 91.5 over from 171 is 262.5. So 262.5, that's halfway between that number and 5 right there. And that is a full cycle here for this year for sunrise, not for sunrise, the amount of sunlight from sunrise to sunset, but the amount of sunlight that there is on any day in the year right here. This is a very, very non-steep curve. And it's going to go back up and do its thing. Sorry for the rough, non-smooth drawing there. But that's the idea. It fluctuates there, and that makes sense. Longer days later in the year. Now, does this account for daylight savings time? I suppose at some point it has to do some sort of shift thing there. That's one thing I'm not accounting for in the model, and I apologize for that. I don't know how to reflect. Actually, daylight savings time doesn't matter. That's just a shift in time. I take that back. Except for maybe on a single day. No, it's middle of the night. Daylight savings time I don't think matters for this stuff at all. Okay. Sketch a graph of the function. So this would be your h of t, and this would be your t right here. This is the hours, not height. This is the hours of sunlight in the day at some day in the year. Okay, write a cosine equation for h of t represent at the summer solstice. The summer solstice is this, value right here, where the h is 171. That's 171 days after New Year's. That's going to be the h value there. The k value is our 12.25 number right there. That is the midline. We still haven't found, I don't think we did. Did we find the amplitude yet? Not really. We found the distance between. But what is what's 15 minus 12.25? That is 2.75. So your A is 2.75, that. And then your B value is based on P. P is this period here. Well, the period, I think it was 366, right? The period between any two times in the year here, it should be 365 on this year, but it's going to be 366 in general. So P is 366. B is going to be 2 pi over our 366. Now that can reduce to pi over 183, like that. So this equation is going to be h of t equals, oh, by the way, this is a positive cosine value because we start above the midline right there. So our amplitude, our A is 2.75. That's distance, 9.5. I want to make sure that is distance. Yeah, that's distance from the midline to summer solstice or winter solstice or whatever. 2.75 times the cosine of our B value, pi over 183, times t minus 171 plus your k value of 12.25. So that ends up being, there we go, that ends up being the equation for that guy right there. We're getting the A, B, H, and K. I used the calculator a couple times there. All right, let me plug that equation into my calculator. Never mind, I don't need to yet. But how many hours of sunlight is expected on April 28th? That's the day that I'm recording this. 117 days after New Year's. Well, the graph I drew isn't great, but let's predict it based on that. How many hours of sunlight were today? You can look it up. I'm sure it won't be exact because this is, a model, but 105, 110, 115, 117 days after. So I'm expecting somewhere around 13 to 14 hours of sunlight that we had today, if my graph is any bit accurate as far as an estimation goes there. So I'm going to substitute 117 in for T right there for April 28th, and let's see how that one panned out here. This will be h of 117 equals 2.75 times the cosine of pi over 183 times 117 minus 171 plus 12.25. I'm going to go ahead and substitute that in my calculator straight up. I'm not trying to reduce little bits now that I have the calculator for this one. So I'm going to do 2.75 times the cosine of pi over 183 times, oh, by the way, I need to be in radians now. Now I need to be in radians here. Times 117 minus 171 plus 12.25. 9.83. Well, I expected something different. What did I do on that one? 9.83. So 9. Man, that's not even close to the answer. Let's see. 2.75 times cosine of pi over 183. I took 2 pi over 366, which was my period there. Let me quickly investigate that one and kind of see what I just botched there. Okay, I think I saw it immediately. I have a typo. I think this says 17. This should say 117. And that's why it's good to look at your answer before what I should have previewed on the graph there. There we go. There we go. That was a lot better. 13.9. I was like, I didn't trust what I said there. All right. Trust the math. I just can't trust the calculator. So so it's about 13.9 hours of sunlight right there. And what did I say? Somewhere between 13 and 14 right there. Okay, so maybe that's how much we got today of sunlight. How many days after New Year's do we expect to have 12 hours of sunlight? So 12 hours of sunlight. So 11, 12. It's really close to that 12.25, right? So probably somewhere in this range, probably somewhere around the 65, 70, whatever time. And there's another time right here at 12 that's probably around 265 or something like that. The idea is they're both the same distance away from here, for example. Or they're the same distance away. I'm going to get a value actually. That one's going to be kind of tougher. I mean, you have a calculator here, but it's going to be a little bit tougher to answer. We have to say how far away it is from... Well, we can say how far away it is from 171, and then we can go the other side of 171 and do that. That's fine. I'll use a calculator at that point. So 12 hours of sunlight, I substitute 12 in for h of t. And this will be 12 equals, this is the last problem, by the way, 2.75 times the cosine of pi over 183 times t minus 171 plus 12.25. I'm going to subtract 12.25 from both sides. That looks like it's negative 0.25 equals 2.75 times the cosine of pi over 183 times t minus 171. Okay, divide both sides by 2.75. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Negative 1/11th. Negative 1/11th. I'm reducing that fraction. Equals cosine of pi over 183 times t minus 170. You can tell I'm ready. When I'm writing like this, you can tell that I'm ready to finish. I'm going to take the inverse cosine of both sides, and I'll get pi over 183 times t minus 171 equals the inverse cosine of negative 1/11th there. I'm eager to see what this is. I'm going to multiply both sides by 183 over pi. Whoops. By 183 over pi. And we'll get that. And then I need to add 171 to both sides. 171 plus 171. So ultimately it's going to say t equals 183 times the inverse cosine of negative 1/11 all over pi. That's pi. That's 11 over 11. And then plus 171 right there. That's an exact answer as far as how many days doing to whatever. Let's use the calculator and see what we're going to get for that one there. So I'll do 183 times the inverse cosine of negative 1/11. Oh, see, I tried to type 2 ones in a row and it didn't work. All over pi. And then plus 171. Okay, 267.8. Now that actually got me the second. Oh, it got me the second one because we were 171 shifted over. So it's actually getting me this one right here, that 267. That was actually really close. 267.8. That's the 267th day, I guess. We can say day 267. I guess, unless we round up. This is kind of a tough part to talk about because do we cut off the number and how do we use it for whatever else? I'm just going to go ahead and say 267. So T is about 267. I'm not going to use days into the year there after New Year's. So that's one of the answers there. Now that's the one that was further out because it came off this inverse cosine equation, which came from 171. But there's another one over here. And the way that you find it is you want to find the distance between these two. And then the distance between these two would be symmetrical. So you can then take that out. So what's the distance between, and I rounded this, but 267 and 171? Well, I probably know. I just don't want to do it right now. 267 minus 171. It's around 96. So I got to do 171 minus 96. That's going to be 96 days before the summer solstice and after the summer solstice. So around day 75. So 267 days into the year and 75 days in the year. I forget what I predicted that it would kind of be based on my drawing before. Let's see where I put it. Yeah, that's I said somewhere 65 and 70, but it looks like it's a little more over here. 75 like that. So, okay, it's 75 right there. 12 hours of sunlight from 7 a.m. to 7 p.m. or something like that. Okay, those are the two ones there. Yeah, this one becomes a little bit of a challenge. It can pose a challenge for you based on what it is that you're doing in the situations, right? The calculator stuff can be kind of hard there. But I hope that covered the gamut of everything we've done so far in this unit. This is Mr. Robinson. Thank you so much for watching. Take care. See you in the next one.